Good evening, everyone. Welcome to the online discussion on water and wastewater treatment. This course is being taken by Professor Bhanu Prakash Belenki from IIT Roorkee. My name is Maniatnam Prakash, and I am from IIT Kanpur. Welcome to the big 10th of online discussion. So, as usual, this is no two more discussion session are left. So, for next two session, we will be using this same link, and the recording of this session is being uploaded on this YouTube channel, which has been already shared with you. So, in week 10, we continued with hardness. So, if you have attended last class, we have seen a detailed discussion. Miss in your normal lecture also, there was a brief detailed discussion about hardness, and during online discussion we discussed about different method to find hardness, different formula in how to find hardness in exams or in lab, or in if how you can calculate the hardness in theoretical way or in experimental way. And this hardness is a very important drinking water parameter, and this drinking water parameter, this hardness should be within the permissible limit as per IS code 10500 2012. Then we discussed, then there was some discussion about water softening method. So after treatment, water may be hard yeah, there would be some element present in there which we have to remove. So there are some process, and the overall process is known as water softening. So there are many process. So one of the process is lime soda softening, where we use lime. Okay, then there is something called recarbonation. So recarbonation is done to adjust the pH of the system, and uh, this is to adjust the pH of the system. There is one question related to also. Then type of softening, basin, and adsorption. So in today's session, all the questions are related to hardness and lime soda softening and lime soda softening too. There is no question related to adsorption, but at the end of the lecture, I have kept some slide to discuss about what is this adsorption and all. Okay, so if after discussion, if time persists, I will be continuing with the adsorption, or else we will stop at the end of the we will stop our discussion till discussion of the some important question related to your assignment. So, and also remember, this question is this question you can expect them in your final assessment exam, or the assessment which you must be giving in uh, you you might be giving during this online session. Okay, so some important question and concept in the Big Ten. So before discussing this question, I wanted to recap something which I have discussed in week 8 या week 9 lectures. So it was something about pH. So actually, whatever the question is being discussed here is related to this pH thing only. So see, whatever this be it hardness, be it alkalinity, or I have to remove any certain element, it all depends upon the pH of the system. So before knowing what are those, how to remove those species, yeah, how to control those species, so it's important to understand what is the pH of the system, because we know we have in last lecture we have seen that this hardness is due to calcium, magnesium, miss multivalent ions. Now suppose the pH of your system is very high, say it is 12, so there is high chances that calcium and magnesium will be precipitated. So it's already in another form. So treating those calcium and magnesium will be very hard for you, or pH will is very low. So these are very important thing which one should know, means how the pH of the system control, means how the pH of the system controls the different species present in the system. So if you look in the broad way, this pH is itself is uh, needs a discussion of more than 4 and 5 hours. So when we were studying, there is one course known as physiochemical course. So when we were studying those course, so our instructor took around more than 4 lectures, yeah, 4 5 lectures, and each lectures were around 2 hours. So you can imagine he took around 10 hours total. So he started with some basic things, and then he moved on into something which is called a speciation of different species. So if something is added in water, so what happened that it dissociate in different forms, and the dissociation all depends upon the pH of the system, and there is something called pK1, pK2, pK3 depending upon the which kind of acid is there. So if certain pH suppose if there is one pK value, and it has one acid has two forms, so which species will be more dominant in the water will all depend upon the pK of the system. Okay, so I will be discussing this thing in more detail way in further slides. But before going to that, before going to in that, so in laboratory, what we do that we generally measure pH with the help of probe. We have a glass probe that measures pH of the system, which is very easy to know. The real challenge is we have to calculate theoretically. Miss, if you know the, suppose if you have a water, yeah, if you are treating a water and you know the species that these species are present in the system, So you have to calculate, you can calculate the pH, but this is not challenge. The challenge is that somehow we have to measure the pH of, we have to know the pH of the system, and the best way is to know the pH of the system is to measure with the help of probe. And based on the pH of the measurement, we have to decide the treatment process, like if the pH is very high, which process, which treatment process I have to adopt. If the pH is very low, means which sorry, if the pH is low, which treatment process I have to adopt. So it's all depend on the pH of the system. So it's important to know the pH. Okay. So generally pH is governed by, whenever we talk about the pH, two things come, that is acid and base. Okay. So any chemical which is added in the water results in the pH decrease. So if you have miss, what is pH before pH means, like there, you should know that there is some water characteristics known as pH. Now, if acid is added in the water, what will happen, that pH generally varies from 1 to 14. Okay, it is pH is between, sometimes say 0 also, but 0 is too acidic. So from 0 to 14. Okay, any base in chemical which now what will happen, that and pure water has a pH of around 7. Okay, pure water has a pH of around 7. So what will happen, that if you add acid in the system, what will happen, that your pH will decrease. It will decrease from 7 to say 1, 2, 3, 4, depending on the type of acid. It is whether a strong acid or the concentrated acid. And on another hand, when base is added, its pH increases, and it can increase from 7 to 14. Okay, so these are two things. This is how a acid and base is defined. Okay, so generally what happened, that when a strong is what happened, that these are acid HCl and H2SO4. So why the pH decreases, why the pH increases on addition of base or acid, you will know when you will know the formula of pH. What is the formula of the pH? So you can, from this question you can see that when HCl is added, it is releasing H plus. When H2SO4 is added, it is releasing H plus. So somehow by addition of this strong acid, we are increasing the H plus concentration in the water. And in pure water, we know that the concentration of OH minus is equal to the concentration of H plus. Okay. So somehow when we are adding this acid, so it is increasing this H plus concentration. Okay, similarly when base is added, so what happened, that when base is added, it is increasing the OH minus concentration. Or you can say that we know that this H2O, this H2O is this H2O is in equilibrium. So as it is in increasing OH minus concentration, so it will decrease H plus concentration. Okay, so with by addition of by addition of acid, we are increasing H plus concentration, and by addition of bases, we are decreasing H plus concentration. Okay, I hope this is clear to you. So what happens then, whenever something is added to water, it will it will there will be some equilibrium constant around which this acid or base will this dissociate. So what happens then, whenever water dissociate in H plus and OH minus, it dissociate at a equilibrium constant of 10 ki power minus 14, and that is known as Kw. So this is an equilibrium constant. Okay, so what will happen, that remember generally, and we know that equilibrium constant is written in the form of reactant, sorry, product divided by reactant species. Okay, and this curly bracket is known as activity of a species. So till now, when you were studying in 12th class, generally what happened, that they were saying it is concentration of H plus. Okay, and they were using a square bracket. But when you study further, there is one something called activity of the species. So what is this activity, I will discuss in later. But for now, you should know that we do not represent our equilibrium constant in form of concentration, but we represent it in the form of activity of the species. And so and it is said that for pure water, this activity coefficient for pure water is 1. Okay, So this will be given by H plus into OH minus divided by 1 is equal to 10 to the power minus 14. So H plus plus OH minus is equal to 10 to the power minus 14. Okay. So this is, remember, this activity is related to this concentration with the help of something called activity coefficient. So this I is equal to activity coefficient into Ci. Okay. And this activity coefficient can be calculated by there are some equation which is given in some standard book such as water chemistry by Benjamin. So at the end of the lecture I will share you the book. You can download it, you can read it in detail. So they have given some equation based on the species present in the system. You can calculate the gamma, and you know the concentration. Generally when we perform some experiment, we always measure the concentration. So if you know the concentration of that thing, you can calculate the gamma, and based on this gamma you can find the activity of that species. And the equation which is used to find the activity coefficient are these three equations. There are several equations, but these are very common used equation. Okay. So for our discussion we will keep this activity is equal to concentration. Okay. So if you want to know more about this activity thing, you can refer to some standard book. But as of now I will be sticking to one thing, that is activity is equal to concentration of your species. Okay. So the next question was how this pH is defined. So many book has defined pH in very different way, but there is one single definition of the pH, and pH is defined as minus of logarithm of H plus activity. Remember, H plus activity. Some standard book will always write H plus activity, but for our discussion we have assumed that activity is equal to coefficient. So the pH will be minus of log of H plus concentration. Okay. And now you can answer this thing, that there was this question na ki why this addition of acid increase pH decreases. So what we were saying, that addition of HCl will increasing the concentration of H plus. So as H plus will be increasing, as H plus will increase, so this value will also increase, but as it is a negative sign, so overall this pH will decrease. Similarly, for the when base is added, what happens, that H plus decreases. So this H plus decreases, this overall decreases, but as it is there is a negative sign, so the pH of the system will increase. Okay. I hope this is clear to you. So remember, always to always, if someone asks you what is the definition of the pH, you have to say in a single line that pH is equal to minus of log 10 H plus activity of H plus, or minus of log of 10 concentration of H plus. Okay. So this is the most simple definition of pH. The next thing is we have to find the pH of a species. So first question is like, you have taken one beaker and you have added some HCl. Okay. And this how this HCl is prepared. Generally what happens, that in your lab there will be one strong acid whose density and how much pure that acid is given. So what will happen, that and someone will say you to prepare a 10 to the power minus 3 molar of HCl. So based on some calculation, you will measure the pH, and you will get say you if you from the probe, if you have measured and it's come out to be 10 to the power the pH is come out to be 3, so you can say the concentration of that acid is 10 to the power minus 3. But here we are going in opposite way. Means we know that we have prepared 10 to the power minus 3 molar HCl. Okay. So we have to find the pH of that system. So one thing, one someone can say that this H we know that this H plus will reach completely H plus and Cl minus. And so what I can do that, so the when this 10 to the power minus 3 molar HCl will be added, so 10 to the power minus 3 molar HCl will be added, so it will give complete, it will give completely, it will give 10 to the power minus 3 molar of H plus and 10 to the power minus 3 molar of Cl minus. Okay. So based on that I can find the pH of the system. Okay. So if you have joined now, so I have just started the lecture, so I am discussing something which I have already discussed in the past session, and that is about the pH. So today's most of the question are related to the pH of the system. Okay, so before going into the solving solution of the problem, I was just going through something which is called to find the pH of the system. So if you, I think you have already joined it. So miss, you have already. I don't remember actually whether you were present when I was discussing the pH of system. So you can right now you can just. This is just a recap of what I have discussed. I think in week 7 or week 8. Okay. Hmm. So we know that whenever something when we take some sample, the whatever the ions are present in the system, all the positive ions are equal to the negative ions. This is a well known fact. Okay. So what will happen, that one thing which we know that then that when HCl is added in water, it will contain H plus, OH minus, and Cl minus. And we know that the sum of all the positive charge will be equal to the negative charge. So what are the positive charge? Only H plus is the positive charge. And on another hand, what are the negative charges? It is OH minus and Cl minus. Okay. And we know that this H plus and OH minus is given by this equation, that is 10 to the power minus 14, and this Cl minus is equal to 10 to the power minus 3 molar, because we know that this HCl will give completely Cl minus. Okay. So this H plus will be now my final aim is to find the concentration of H plus. Okay. So this H plus will be as it is. This OH minus can be written as 10 to the power minus 14 divided by H plus, and this Cl minus is as it is, that is 10 to the power minus 3. Okay. So if you solve this equation, this you will get this quadratic equation, and if you solve this quadratic equation, you will be getting this 10 to the power minus 3 H plus concentration. So what happens here, that this quantity is very low quantity, so you can directly ignore this and you don't have to solve any kind of quadratic equation. But the challenge will be when this thing is not negligible, because here 10 to the power minus 3, whatever be the pH of the system. Okay. So if it is being multiplied by 10 to the power minus 3, obviously this quantity will be much larger than this 10 to the power minus 14, so that's why it can be neglected. So the challenge will arrive when this H plus concentrate, when this when this 10 to the power minus 14 things cannot be neglected. So here we miss always. I will suggest always to move in a predefined way, that if you want to solve this charge balance thing, you will form one quadratic equation, and based on the quadratic equation you can find the pH of the system. Okay. So the pH of the system will be 10. We know that the pH of the definition is being given by 10 minus log 10 of H plus, and 10 H plus is 10 to the power minus 3. So log 10, 10 to the power minus 3 will be minus 3 and minus 3, and this minus 1 will finally give the pH of the system as 3. Okay. So I hope this is clear to you. So from next onward we will be solving the question where this on the next class I have a question where I cannot neglect this 10 to the power minus 14 thing. Okay. So the question is to find the pH of 10 to the power minus 8 molar H2SO4 solution. Okay. Just 1 minute. So we know that this H2SO4 will give plus SO4. What will this H2SO4 will give? This will give H plus, that is 2 mole of H plus, plus SO4, SO4 2 minus. Okay. So this is H plus into H minus is equal to 20 power minus 14. Okay. So this SO4 2 minus will be 10 to the power minus 8, because this H2SO4, I already know that this will give 2 mole of H plus and 2 mole of SO4 2 minus. So to SO4 2 minus concentration will be 10 to the power minus 8. Okay, and we know that for a given system, all the positive charge will be equal to the negative charge. So this H plus is equal to OH minus. Now remember, this SO4 2 minus is giving 2 charge. Okay, so there will be a multiplication of 2, that is H plus plus OH minus is equal. There will be multiplication of 2 SO4 2 minus. Okay, so I hope this is clear to you. Again, I will be doing same thing. Now here remember, so sorry, in the next step, H plus is at 0, this OH minus is 10 to the power minus 14 divided by H plus plus 2 into 10 to the power minus 8. Okay, so now remember this, I have finally arrived at this equation. Okay, so now see, this is 10 to the power minus 8, this is 10 to the power minus 14. So this thing cannot be neglected now. Okay, because this will be a very significant, this is miss, I won't be saying this is similar, but your pH will be in the range of 10 to the power minus something only. So it will be 10 to the power, say suppose it is 10 to the power minus 5. So it is 10 to the power minus 5 into 10 to the power minus 8, that is 10 to the power minus 13. So it cannot be neglected with respect to 10 to the power minus 14. So that's why this approach and that approach is very similar, but where you have to neglect, you have to keep in the mind. Okay, so if you solve this equation, if you solve this quadratic equation with help of some standard calculator, so you will be getting this H plus concentration as 7.05 into 10 to the power minus 7. Okay, once this H plus is known, you can find the pH of the system, and the pH of the system is 10 to the power 6 9 10 6 sorry 6.97. So remember, this a strong, this is H2SO4 is a strong acid, but at very low concentration it will be termed as diluted strong acid, because the pH is very this 10 6.97 is almost similar to 10 to the power minus 7 only, that is pH 7 only. And we know that pH 7 is very common pH, and this is also the pH of pure water or normal drinking water. Okay, so it, but it doesn't mean that you can drink this H2SO4. All I am saying that a strong acid will be always a strong acid. Only the difference will be there. Either it will be diluted strong acid or concentrated strong acid. Okay. So for example, this 10 to the power minus 3 was a strong concentrated HCl acid. Okay, now concentrated strong HCl. And now imagine that this is 10 to the power minus 8 HCl. So you could have solved this thing. Sorry, you could here, instead of writing this H plus into 10 to the power minus 3, it would have been 10 to the power minus 8, and on the basis of that I would have solved my quadratic equation. At that time I cannot neglect this 10 to the power minus 14 thing. Okay, so I hope this is clear to you. So once I have done it, I will calculate the this pH of the system, and it come out to be 10 to the power minus 1.05 into 10 to the power minus 7. Okay, and the pH come out to be 6.97. Okay, so now these were all about this strong acid. So now something we define something, another type of acid, that is weak acid. Okay, so weak acid, so what was happening in the strong acid? So when we are adding, I was adding a strong acid, so all the H plus and whatever an ion is was present there, they were dissociating completely. So but in this case, what's happening, that it won't dissociate completely. Okay, so now what is, this is acetic acid, where this now this is acetic acid, so this is a weak acid. So what will happen, that when you will add acetic acid in water, it will release H plus and acetate ions. And what will happen, that this the acid which I have added will also contain some of its original amount also, and that is known as this a star thing. Okay, so So it will be this will suppose initially it was added x amount. Suppose total x amount is added. So what will happen that some of this will dissociate in CH3COO minus, but out of x, say by amount will remain as acetic acid. So that is known as aqueous acetic acid, and that is represented by CH3COOH a star. And I have already said that every acid dissociates at some particular equilibrium constant. So what will happen that, and the equilibrium constant from experiment, it has been found that it is 10 to power minus 4.8. Okay. This is 10 to power minus 4.8. So what this pk this Ka means? So now now this pK means that, suppose this is your pH range and this is boundary of 4.8. this is this is a boundary of 4.8. So what will happen that below this pH, you can see that now suppose imagine pH is 4. So pH is 4 means 10 to power minus 4, it will be 10 to power minus 4, and it will be 10 to power minus 4, this will go this side. So means the overall quantity will be less than 1. Okay, so if this is less than 1 means this quantity is dominant. So before this pH, this CH3 CH3COOH means acetic acid is dominant, but after this pH, this acetate ions will be dominant. So we always plot something called log CpH graph. What is this log CpH? I will be explaining in the detail. Means I will be showing more about this. So generally, what happens that to identify which species is dominant at which pH, generally we plot a graph known as log C log C versus pH graph. Okay, so your pH will be from 0 to say 14. Okay, 0 to 14, and here suppose here is your pH, that is 4 point. Here is your pH, that is 4.8. So what will happen that at 4.8, as already said, that the CH3COOH will be dominant. So a graph its concentration will vary like this. Okay, and at higher pH, this will be dominant like this, and at pH 4.8 the concentration of this will be equal. This is what I have shown. So this is corresponding to this CH3COOH minus, and this is corresponding to this. So this is a log CpH curve which we generally follow. Okay. Hmm. Sorry. So what will happen that this pH will be, this is a simple log C pH graph. Okay. So now the next question is how to, uh, means if you have given some water containing acetic acid, you can in lab you can directly dip your probe and you can measure the pH of the system. But the question is, someone has said that that this 10 to power minus 3 molar acetic acid has been given to you. Find the pH of the system. Okay. So in that case, what you will do, you will follow the approach which we were following in the strong acid, that is charge balance. Only thing which we will we will point out that what was happening in strong acid, it was as it was H2SO4. This SO4 was complete whatever was being added, but here this CH3 stable OH, we cannot say that CH3 stable OH minus concentration will be 10 to power minus 3 molar, because we know that this is a weak acid. So out of 10 to power minus 3 molar acid, some of the acetic acid will remain in its original form, that is known as CH3 stable O star. Okay. Okay. Hmm.
So this thing I know that this H plus and OH minus is equal to 20 power minus 3, and the total CH3 schedule OH which is added is referred as Ca, and its concentration is 20 power minus 3 molar. Okay, and this is summation of CH3 schedule OH that is dissociated form and the undissociated form, that is CH3 schedule OH a star. Okay, and charge balance, again this is in neutral species, so the charge which is, will be contributing in the system will be H plus, OH minus, and CH3 double O minus. Okay, this H plus is equal to OH minus plus CH3 double OH minus. Okay, and this and we also know that now remember this thing, we know this equation. My final aim is to find out this CH3 double OH star. Okay, yeah, we miss in the, we have to find, sorry, we have to find in equation, we have to find H plus, and this OH minus is in the form of 10 to the power minus 14 H plus. The challenge is I have to represent it in the form of H plus only and no other thing. Okay, so we know that this CH3 C double total Ca is equal to CH3 C double O minus plus CH3 C double O H. Okay. Hmm. So, and we know that this CH3 double OH can be written as this H plus plus CH3 double O minus divided by Ka. So, this is what I have done here. Ca can be represented in the form of CH3 double OH H C double O minus H plus plus CH3 double O minus Ka. Okay. So, now this Ca will be CH3 double O minus 1 plus H plus divided by Ka. Okay. So, and from here I can write down that CH3 double O minus is equal to Ka Ca divided by Ka plus H plus, and this thing is a constant term. This Ka plus H plus is a constant term, and that is known as alpha 1. So this CH3 minus is equal to alpha 1 Ca. So it is expected that you should know this, what is this alpha 1, and similarly, so now this is alpha 1. So similarly for acetic acid, hmm, I will find out the expression for CH3 to C double OH. You can simply, you know this is alpha 1A. So you can put this value here, and you can find the expression of CH3 double OH minus. And if you do it, you will find out that it is H plus divided by this same constant, say capital K. Okay, and multiplied by this Ca. Okay, and this H plus divided by K is known as alpha naught. Okay, so this CH3 double OH star is known as alpha naught Ca. Okay, so I hope this is clear to you. So this H plus plus OH minus is equal to Ka divided by Ka into Ca divided by Ka plus H plus, and you can put all this value, and if you rearrange it, you will get a cubic equation. Okay, you can see that this will multiply will form quadratic, and here it will multiply by H plus. So you will form a, you will get a cubic equation. So you can solve that equation, and if you solve that equation, you have to use calculator only. So if you solve this equation, you will get three value of H plus. Out of these three value, only one will be positive, other will be negative, and we know that the concentration cannot be negative. So whatever H plus will come out to be, it come out to be 1.202223 into 10 to the power minus 4. So the pH of the system will be 3.92. Okay. So in this way you can calculate the pH of a weak acid. Now remember, this was a H, means this was a monoprotic, means it was releasing only H plus. So now we will look into the system containing 2 H plus. So this is known as diprotic. Protic means H plus, means this acid will be releasing 2 H plus in the water depending on the pH of the system. Okay. So what will happen that whenever you add this H2O, what will happen that this H2O will form this Ha minus, and it will give H plus. So it will happen at around 10 power pH 10 power minus 6.3, and similarly again this Ha minus will dissociate in the this A2 minus and H plus. Okay. So again here you can plot this CPH log CPH graph. Miss this is your pH line. This is 6.3, 6.3, and this is 10 ki power. This is 10 point 10 ki power minus 3. Okay, this is 6. Hmm. So at this pH, what will happen? That you can see that at this what kind of equation you can write? Sorry, you can write the equation as this Ka1 is equal to Ha minus Ha minus into H plus divided by this H2. Remember again, as this is big acid, big diprotic acid. So all the H plus this H2O will not dissociate. Some of will be still in its original form, and that is known as H2O a star. Okay. So now imagine the pH is around 5. So what will happen that this is 10 to the power minus 5. You will put it here. It is greater than less than 1. So it will be here. You can say that this here H2 a is dom H2A is dominant. Okay, sorry, this H2A is dominant. Similarly, what will happen that if you put value here, yeah, you can use any equation. Here you will see that this HA minus is dominant, and here you will see that this A2 minus is dominant. So you can plot this log CPH graph here. So this is your pH system, and this is log C. Here you will draw one line. Here you will draw one line. It will be 6.3, and here it will be 10.3. So here what will happen that this will be a strong acid, so its concentration will, sorry, this will be dominant here, so it is corresponding to this thing. And similarly what will happen that this will dominant and it will form like this thing. So this is corresponding to this A minus. And remember at pH 6.3 the concentration of this and this will be similar. And similarly for pH greater than 10 to the power minus 3, this A2 minus will be dominant. Okay. So this is log pH. You can refer one book which is a very standard book, that is by hmm, that is by Benjamin. You here you means they have developed equation and how this with pH how this form. You can a very detailed analysis is given in that book. Okay. So this is log CPH graph. So I will just erase it. So now the question is to find the pH of this 10 to the power minus 3 molar H2O H2A solution. Okay. So again similar to that, what will happen that this Ca will be in the form of H2A plus Ha plus A2 minus is equal to Ca, and we already know this thing also, and I have already said that define two things, that is alpha note alpha 1. This is alpha note alpha 1 and alpha note. Similar to that only, here we will define two things, that is alpha note alpha 1 and alpha 2. Alpha note it will be corresponding to this H2A, and it will be given by same expression. Just remember there what we were writing, H, it was in H plus, and it was H plus plus K1. So as K1 K2 will be keep adding, this term will be keep extending. So for this diprotic acid, big diprotic acid, what is happening, this alpha 1 will be given by this equation, alpha naught 1 will be given by this equation, alpha 2 will be given by this equation. And this charge balance, we know that this is H plus H minus plus H plus 2 A2 minus. And you can use this equation. So now what your aim is to convert this overall equation in the form of H plus only. So and you have two relation. First relation is this thing, second relation is this thing, third relation is this thing. So what you can do that here, you can substitute all this a plus and a2 minus in the form of this ca and h plus with the help of all these three equation. So how can you this thing, this a ha2, this ha2 can be written in the form of ha minus plus h plus. And so you can substitute here that thing with the and this ha minus will be as it is. And with the help of this equation you can substitute this a2 minus in the form of ha and h plus. Okay, so here you have already written in the form of ha minus and a sorry, there is no need to write this a2 minus in the form of again in the form of, you can write also, it doesn't matter. Okay, so you will put all this value, and you whatever you value you get, you substitute here the ha minus. And similarly for a2 you can substitute here whatever value you are getting from here only. Okay, so this is very simple thing, this is just a mathematics thing, there is no chemistry, yeah, there is no environmental thing related here. Okay, and this h plus will be now this h plus will be given by k1 plus h plus alpha 1 Ca 2 alpha 2 Ca. And you know this alpha 1 alpha 2, you can substitute it and this will form a fourth order equation. Okay, so you can solve it by, you have to use now generally what happens, there is a normal calculator, I don't know which kind of calculator I'm talking. Fourth order equation cannot be solved, so you have to use excel, and if you use excel you will get the pH as 5.69. Obviously from this equation h plus will be known, and from there h plus you can calculate the pH. And the h2a star, h8 minus and a2 minus can be calculated, because you know this alpha 1 alpha 2 c and all this thing. So you can calculate the concentration of this h2a h2a and other thing also. Okay. Hmm. So again, what I was talking about this thing, log CPH graph. So I have taken this from this Benjamin book. So you can see that they have talking about this weak acid. Okay, so this HOCl, ammonium, and this acetic acid, this CH3 sheet always. So you can see that for acetic acid the pH is around 6, pK value is 4.8. So you can see that before this line this HAC bar dominant, and after this pH this acetate ion is present. Similarly for this ammonium you can say that its pK is around 9.1 or 2. So before 9.1 this ammonium was dominant, and after 9 it was ammonia which was dominant. So what is the real world application of this graph? So now you know that there might be chances that your water is contaminated with ammonia, and the question is you have to treat ammonia. So before treating ammonia you should know that in which form ammonia is present, whether it is in ammonium ion or it is in NH3 form. So what you will do, that you will measure the pH of the system, and you will measure. So you can say that the if the pH is below 9.2, so you will say that the ammonium ion is dominant. So I have to remove that ammonium ion in the, so you will add that kind of chemical which will treat ammonium. Or you can miss huh, or there can be other kind of situation where you know that this presence of ammonium will release ammonia. So you don't want your system to release ammonia, so you will make sure that your pH is always below this 9.2. Okay, similarly for this OCl minus, this OCl minus is greatly used in disinfection. So this HOCl and this is OCl minus, and we know that particular form of OCl minus can treat your disinfect your water. So generally it is OCl minus. HOCl generally do not disinfect our system. So you have to make sure that the pH of the system is in a such a way that this OCl minus is dominant, and the OCl minus is dominant, and you can add your chemical in a such a way that this OCl minus will be dominant, and this will help in the disinfection process. Okay. And similarly, this was for big monoprotic acid. Similarly, for big diprotic acid, you can see I have plotted for this carbonate ion. So this is 6.35. So it is 6.35, and it is 10.333. Okay, so you can say that below this alpha note, and this alpha note was corresponding to which thing? Alpha note was corresponding to this H2OA. Okay, is dominant, and this was sorry, this alpha naught was according to the H2A, means this acetic acid is dominant here. Okay, you can see that this is acetic acid is corresponding to alpha naught. This now alpha 1, the variation of alpha 1 is corresponding to HCO3 2 minus, and finally fully deprotonated form is carbonate ions, and this variation is so miss you can miss you can you there is no need to mug up this graph. You can just imagine how this one two three things you have to make sure that at pK the concentration of the ions to corresponding ions will be same. It is always a smooth curve, and that's all. Okay. At remember at one more thing, at any point the summation of alpha naught, alpha 1 and alpha 2 is always equal to 1. Here they have taken log thing, but you can just draw a line here. Whatever this alpha naught come out to be, alpha 1 come out to be, and this alpha whatever this, you can see you will be getting these two three value corresponding to alpha naught, alpha 1. So here for alpha 1, here for alpha naught, and here you can see that it will meet this. You can see that this summation of all these three things will be hmm, thing will be always equal to 1. And you can check also these things. You can just put it value. You can see that if you add all these things value, this plus this will be equal to, and this should be obvious thing, because we know that this is summation of this summation is equal to CA, and you will put value here, so CA will be cancel out, and you will be getting alpha naught, alpha 1 and alpha 2 is equal to 1. Okay. Similarly, for C, this is for phosphate H3PO4. So here it is a triprotic acid, big triprotic means it is leading 3H plus. So its pK one pK value is 2.16. The second pK value is 7 point this thing 7.20. Third is 12.35. So you have around total four range. One first range, and the first range H3PO4 will be dominant. Here H3PO4 H2PO4 minus will be dominant, and here HPO4 2 minus will be dominant, and finally here PO4 3 minus will be dominant. Okay, I hope this is very clear to you. Hmm. So, and the real world application is again the same thing, that you have to treat phosphate. Then before treating it, you should know that which form of phosphate is there, so that I can remove it. Okay. So generally pH, drinking water pH has a range of 6.5 to 8.5. So here you can, in that range you can say that this H2PO4 and HPO4 2 minus both will be dominant depending upon the pH of the system. Okay. Hmm. So coming to the first question which is there, is this thing related to this dominant species only. Okay. And I have already said this thing also, that high presence of high OH minus and can precipitate magnesium and all this thing also. Oh, also you have to match the following. There are four pH different condition and four different thing, and you have to answer according to that. Okay. So the first question is first thing is that related to this dominant species of S3, S2CO3 and SCO32 minus. Okay. So this thing I have already explained you. This is PK1, this is PK2, and below this PK1 that is 6.35. This H2CO3 star will be dominant. Between this pH SCO3 minus will be dominant, and greater than pH 10.3 this carbonate will be dominant. Okay. So the first question is like this pH 10.10 at pH 10.5, at pH 10.5 which will be dominant carbonate, but there is no such ion. So means first is matching with, first is no won't be matching with these or this thing. Okay, at pH 10.5, at pH 10.5 you can see that again this carbonate will be dominant. Okay, so again, this won't be matching with any other option. But at pH 7.5, 7.2, that is this thing. This alpha one is dominant. Means this carbonate bicarbonate is dominant. So this third option will be matching with D option. So means these two answer can be correct answer. Okay. And the last option is at pH 4.1. At pH 4.1, you can see this alpha note is dominant. That is bicarbonate in non-protonated form. Okay. Hmm. So this four will be matching with A. So without matching option one and two, you can answer that this is a correct answer. But still we will be discussing the option number one and two also. Okay. So what happened that option? Uh-huh. I have written something wrong. Correct option is A. First card D. No. This is A. Correct option is D. Hmm. Hmm. So what will happen that at pH 10.5, what happened that the concentration of this OH minus is very high. So and OH minus has a tendency to react with and to form a, there should be one S here. Okay, solid. So it will Mg will react with OH minus present in the system. I have written wrongly. Always make sure to write your reaction in a very scientific way, because if someone is checking to you, so what will happen that what happened that when sufficient OH minus is present and Mg is also present, so it creates a thermodynamic condition in which what will happen that is MgO will react with OH minus and it will form a MgOH solid, which is a solid form. Okay, which is in a solid form. So at this pH, this as pH 10.5, at this pH 10.5, this Mg2 plus and OH minus will react and it will form this magnesium precipitate, magnesium hydroxide precipitate. Sometimes it is also known as brucite, brucite, BRUCI, BRUCI. T E. Okay, blue side. Okay, so this Mg2 plus 2OH minus plus MgOH solid will form a this thing, that is Ksp 10 to the power minus 10.9. Okay, and similarly what will happen, this calcium at pH around 10, this calcium we know that at pH 10.5 this carbonate 10.5, this alpha 2 will be dominant, that is carbonate will be dominant. So it will form, sorry, it will be hmm, this carbonate will react and it will form this thing. So a question can be asked that why OH minus will also present at pH 10.5. So why cannot happen that means actually yes, calcium hydroxide will also form, but it has more tendency, yeah, it is more favorable depending upon the due to this Ksp constant. Okay, so you should know that there is something called delta G. So all this formation is dependent upon the delta G. So delta G is more negative for this formation than rather than formation of calcium hydroxide. Similarly, for here carbonate will be also present, but the formation of calcium magnesium hydroxide is more dominant as compared to formation of magnesium carbonate. Okay, so the correct option is D. Okay, so this will be matching with magnesium, this will be matching with B, this will be matching with D, and this will be matching with A. Okay, so I hope this is very clear to you. Now the second question is, lime is not required to remove which of the following. So see, this is you have to know the thermodynamics, which kind of reaction occurs and how those reaction occurs. So I will try to give you some insight, like how this formation happen, how some form of calcium react with other thing. So but this is all are theoretical thing. Miss, I won't say you have to mug up those things, but you know the pH of the system and how thermodynamic of the system. You can answer this question. Okay, so hmm. So before answering this question, one should have idea what is non-carbonate hardness, because a question might be arise that this carbonate is due to multivalent ion. So why they are saying carbonate ions? Okay, so I am giving you some a small discussion, a small idea um, about this hardness, which I have also covered in the last class. Okay, the presence of multivalent and ion in mostly notably Ca2 plus and Mg type of hardness. So remember, if this calcium is attached to carbonate, it will be known as carbonate hardness, and if this magnesium is attached to yeah, calcium or magnesium is attached to non-carbonate, miss HCO3 minus, yeah, sorry, other than carbonate thing, then it will be known as non-carbonate or permanent hardness. Okay, you know this thing, this EDTA is used to find the hardness and all this thing. This all you have already know. This is a formula. If you know the calcium, if you know the formula, if you know the concentration of calcium present in the system, magnesium or all other things such as aluminum, iron, you can calculate the hardness. Okay, so the correct answer of this question is A. Why it is A? See, more detail has been already discussed in the your online session. So I am just reading. I have taken this thing from there only. So the correct answer is calcium non-carbonate hardness. Why this calcium non-carbonate hardness? Lime or is not required to remove, because this calcium non-carbonate hardness is a, what I said. This is a temporary hardness, and temporary hardness can be Uh, this temporary hardness can be removed by simple boiling. There is no need to add some kind of chemical and all this thing. Okay, so that's why what is happening that this lime or carbonate hydrogen is not required to refers to the presence of calcium and removing calcium and different treatments such as exchange or precipitate rather than this thing is incorrectly. I have written it incorrectly. Okay, you can see simply say that this calcium calcium non carbonate hardness can be easily. Oh no, no, sorry. I have written it correctly. This is they are talking about non-carbonate hardness, and non-carbonate hardness cannot be removed just by just simply adding some chemicals. You have to you have to go through some special treatment such as use of ion exchanger and all this thing. So this is what I have written here. Remove involve different treatments such as ion exchange or precipitation with some other chemical. But what happened that how this lime is used to treat hardness, you have to go and read this your online session. Okay, so the correct option is here. Lime is not required to remove calcium non-carbonate hardness. Okay, what which is the following the correct criteria for effective water softening? Okay, so how the first of all you have to know how this water softening is done. Okay, water softening is done by addition of carbonate. Okay, so water softening, first you should know what is water softening. So water softening is a process of reducing the concentration of calcium, magnesium and other divalent cation in the hard water. Or you can simply say that if you have hard water, you want to make a soft water. So the water softening is a process which is also referred as to remove the hardness of the water. Okay, so how hardness can be removed? So if you remove this calcium, magnesium or other divalent metal ions, other divalent metal ions, you can remove this hardness from the system. Okay, hard water contains high amount of calcium, magnesium, which can lead to various problems such as scalp building in pipes, appliance, and reduce the soft leathering and formation of soft scum. Water softening mitigates this issue by removal. And someone can ask why removal of hardness, because this is not an economical thing. Because what will happen that it will be at those water contains calcium. So what happened that with time this calcium precipitate on the pipe of butter supply, so making it making it non-economical thing. So and generally due to presence of this calcium and multivalent ion, the soap which be used for bathing purpose here, bathing purpose here for washing purpose, won't form any kind of scum, and which is not good for washing or bathing. Okay, so we have to make sure that a sufficient amount of scum is produced. So how you can check how this presence of calcium affect the formation of a scum and all this thing. You can go and you can watch any YouTube channel, a YouTube video. You can see can know there. But a water which is hard will always cause some kind of uh, economical. It cause some economical loss. Okay, so there are several methods that one is ion exchange method. So the ion exchange is this is one of the most common method. It involves passing hard water through a resin weight containing sodium ions. Their resin exchange sodium ions for calcium and magnesium, effectively softening the water. Okay. Periodically, the resin weight needs to be regenerated. So this is kind of a ion exchange method. So what will happen that mm, so generally this kind of system is there. It will contain some kind of resin here, some kind of resin will be here, and it will contain, so water will be poured from this side, and there will be some ion exchange happening here, and you will get a soft water. Here it will be hard water, and here you will be getting a soft water. Okay, The other is lime softening. The lime softening is added to what is added to causing calcium and magnesium and to precipitate or soluble carbonates. Okay, so remember. So here I have said this thing. The, this magnesium can form OH minus and a carbonate thing. Okay, so this lime will be giving. Again, I have made one mistake here also. Always make sure to write to show the precipitation. Always make sure to write this thing. Hmm. Okay, so resulting in and in that, so now suppose if you want to do one best method is that somehow we have to precipitate. So adding of calcium, what will happen that it will release a high amount of OH minus, and that OH minus can react with magnesium and carbonate also. Generally it does not react with calcium. Okay, so but the carbonate present in the system, as pH is lower, this calcium can react with carbonate and it form calcium carbonate. And at high pH we know that this OH minus will form magnesium MgOH whole twice. Okay, remember, one is forming magnesium is forming hydroxide and calcium is forming carbonate. Okay, then other is reverse osmosis. This is a filtration process that remove ions, molecules and particles from the water using a semi-permeable membrane. Reverse osmosis can effectively reduce the hardness, but here same thing happen that I think everyone has seen the apparatus for uh, reverse osmosis. So a setup is like this. There is one membrane here, so hard water is added here, pressure is some pressure is caused, and due to which what happened that calcium, magnesium and multiviolet ions will get trapped here. You will get a soft water at the end of the tank. Okay, reverse osmosis. So and third is distillation. This is just to remove temporary hardness. So, but that is carbonate hardness. So you can see distilling over heating water, which then condensed in the liquid. This effectively remove mineral including calcium, magnesium, leaving the water softened. Okay, so what will happen that if you heat it, all the calcium and magnesium will precipitate out and you will get a soft water. Okay, water softening is important for various application including household use, industrial process and agriculture, and it prevents the uh, somehow we have to prevent this problem which is due to the due to hardness. Okay, coming to the question, line dosage should be greater than total alkalinity plus total plus dissolved CO2. So we know that in a water there will be some dissolved CO2, because this CO2 will be giving carbonate, bicarbonate and other ions of carbonate, and this, and we know that about alkalinity, and alkalinity is due to carbonate only. Okay, so how much lime should I add? So it is said that you have to add that much of lime that will remove the dissolved CO2 also, and that will also remove the alkalinity also. Okay, because we know that by adding lime, I will be precipitating all the carbonate and OH minus present in the system in the form of MgOH and calcium carbonate. Okay, and from where this carbonate is coming, the carbonate is coming from this alkalinity, and because we know that alkalinity is only due to carbonate, bicarbonate and caustic thing, that is OH minus. So when treating water with lime calcium hydroxide for softening, it is essential to ensure that lime dosage provided is sufficient to react with both total alkalinity and total dissolved carbonate in the system. This ensures that all alkalinity and CO2 are neutralized and removed effectively. Therefore, the lime dosage should be greater than equal to the sum of. Okay, so all thing. See, if you have any kind of confusion with total alkalinity, you can go back and check out the previous video lecture which I have uploaded in the YouTube channel. Okay. Hmm. The recarbonation, again, see, remember this recarbonation I have shown you. Why, what is this recarbonation? There was a question related to this recarbonation. Okay, I don't know where was that. Yes, okay, I will. So just recarbonation is addition of CO2 in the water. So what will happen that this CO2 will form this CO2 gas will form H2CO3. Okay, and this H2CO3. So what will happen that how this CO2 dissolve in the gas is depend upon the Henry constant. Okay, this KH is Henry constant, and that is 28.8 atm per molar. So we know that any gas will dissolve in water depending on the partial pressure of the atmosphere. Okay, so this H2CO3, and again what will happen that this H2CO3 will result in the formation of HCO3 minus, and it will release H plus ions, and again this will dissociate in the form of carbonate and bicarbonate. So all here you can see that all this process is just increasing the H plus concentration. And what was the definition of the pH? Definition of the pH was, oh, I am not written it. The definition of pH was minus log to the base 10 into activity of H plus. Okay, H H plus, and now this H plus is increasing. So this H plus is increasing means this overall quantity will decrease, means pH will decrease. So the correct answer will be P, the decrease in pH to acceptable level. Okay, so generally what happens that in wastewater treatment, suppose you have treated water and it come by addition of some chemicals, say basically if you add, suppose you have added lime. So if you have added lime, so obviously this will increase the pH to around 10, 12, and you cannot supply this water having pH 10 to, because we know the acceptable limit of pH is around 6.5 to 8.5. So you have to make sure that the pH of the system is around this thing, that is 10 point, that is 6.5 to 10.5. So to adjust that thing, we decarbonate. We add some CO2 in the water, so that will finally that will result in the decrease in the pH of the system, and your whatever was your target for treatment of the water can be achieved. Okay. Coming to the another question, corrosion of pipes may occur if water is with carbonate, where scaling in the pipe may result, which is blank with the carbonate. Okay, saturated, undersaturated. So first you have to know what is saturated condition, what is undersaturated condition. Okay, so I will be explaining something related to saturated and undersaturated. Okay, saturation in the context of water chemistry refers to the state where a solution contains maximum amount of dissolved solute that can be dissolved in under specific conditions, such as temperature and pressure. So now you know that, yeah, suppose you have taken one water. Now you have started to add salt. So what will happen that, suppose you have started to add salt NaCl. So generally what will happen that all the water NaCl that is there, it will dissociate in H plus and Cl minus, and it will completely dissolve. Okay, yes, completely dissolved. But now you are keep you are being what you are doing, you are just adding more and more NaCl. So at a point, what will happen that this water cannot take any more Na plus and Cl minus. So what will happen that whatever you have added NaCl, it will precipitate out, it will remain its in original form. Means this system is saturated with NaCl, means this system cannot take any more NaCl. So that is known as saturated condition, means this water has already saturated, it cannot dissolve any more Na and Cl minus. Okay, so this was one way to explain. Another way to explain is that you are performing some kind of experiment, and you want to precipitate something, suppose AB is any kind of salt. Okay, so how you will make sure that you have to precipitate AB? So in water you will start adding AB plus AB salt, A, and similarly from another end you will start adding B. So what will happen that this a plus a plus suppose a plus and this is b minus. Okay, so this a plus and b minus will react and it will form a. This will form ab, and when the this ab form, when this system is super saturated with A and B, means whatever dissolves initially A and B were dissolved in form. Now what's happening that this water cannot take more A and B. So what will happen that this A and B will start forming, and it will start forming a AB solid. So after some time, by adding more A and B, you will be getting a salt at the bottom of your beaker. Okay, so this is what happened, this is what it is written here, that maximum amount of dissolved solute means maximum amount of A and B that can be added under a specific condition. When solution is saturated, it is equilibrium with undissolved solid. So when this is unsaturated, and meaning that additional means what it has attained equilibrium. So addition of solid to the will not dissolve, but instead it will precipitate. Sorry, here is it will instead precipitate out because the system is saturated with the system. The system is saturated with the specific salt that is present in the system. Okay, so one term is defined, that is saturation index. Saturation is it talks about the saturated condition of system with one or many solid in. When solid precipitate or not determine the saturation index, and saturation index is given by this SI log 10 Q into KSP, where SI is saturation index, Q is ion activity product, and KSP is solubility product. So we know that this thing, this AB salt is there. Okay, so we know that this AB salt will give AB plus plus B B minus. Okay, and its KSP will be given by this KSP will be equal to uh, activity of AB plus at equilibrium. Okay, AB plus into B minus. Okay, this will be KSP at this is at equilibrium. But suppose at any time, when system is not equilibrium, so it will have some concentration. It will have some concentration, but still the at equilibrium we write KSP. But when the system is not at equilibrium, we define one term that is Q, and that is known as ion activity product, and that will be product of concentration of A and B. Okay, so we will substitute here. We will find miss this KSP is constant for any solid, but this Q miss you can miss from here you can find out how much salt you have to add, so that you will make your system saturate. Okay, so now when Si is equal to 0 means Si is equal to 0 means this Q is equal to KSP, so that's why at this time it will be 0. Okay, so when the system is 0, then we will say that system is equilibrium with that solid. Okay, that solid can be A B. Okay. Hmm. Now, when SI is 0, the system is undersaturated. Means under this KSP SI is greater than 0. Means this KSP is greater than Q. Okay. Means not sufficient amount of A and B has been added, because this is less. That's why Q is also less. Means sufficient amount of A and B has not been added till now that it can precipitate AB salt. Okay, so this is what here written. The system is undersaturated with solid, and solid will not form. When Si is 0, the system is saturated with this solid. Now what happened that you have already added too much A and B. So obviously the concentration of A and B will exceed this KSP, exceed this KSP, and the Si will be greater than 1. Okay, sorry, greater than 0, and your system will be, and remember not only this system has to be saturated, kinetics has to be also favorable. Means what is happening that you have added sufficient amount of A and B, but it is taking 1 year to form. So you cannot say that system is under saturated. System is saturated, but it is taking more time to form because it is not kinetically feasible for formation of AB. Okay, so this was all about saturated and undersaturated. So what you can say that if something has to be precipitate, all the entities should be greater than ks, means the q should be greater than ksp, means sufficient amount of both form of species dissolved solid should be in a such a way that it can cross the ksp value and it can precipitate. Okay, the question was about the corrosion and scalping. The and one should know what is this corrosion. Okay. Hmm. The corrosion refers to the deterioration of metal, typically a metal due to chemical or electrochemical reaction with its environment. I hope this is very common. No, nothing rocket science with this statement. In the context of water infrastructure, corrosion occurs when metal pipes or components react with water substance dissolved in the water, leading to the degradation of solid. So, metal pipes component react with the water. So, whatever the component is there, AB is there, its ksp is its q is much larger than ksp. That's why it is precipitating out and forming some kind of corrosion. Okay, corrosion forms or corrosion in the corrosion form of corrosion in water system include rusting of iron pipes and the formation of pits on metal surface. Okay, corrosion can weaken pipes, leading to leaks, reduce flow. Factors such as pH, dissolvent, all things is very clear to you. Okay. And on other hand, scaling. Scaling refers to the deposition. So remember, this is corrosion means rusting and all these things. Scalping means formation of some white layer, which you miss if you are using some heater in your room, in your home. You can see that there is a white layer on the surface of your heater, water heater, and it is due to this thing only. And the fact is known as, and generally when your water is very hard, all the on heating, this calcium and carbonate will react and it will form white precipitate, and that is known as scaling. Scaling refers to the deposition of buildup of mineral deposits, typically calcium carbonate, on the surface of the pipes application and see calcium carbonate, and this calcium carbonate is white in color. Okay, a scaling occurs when the concentration of dissolved minerals in water exceeds their solubility limit. The solubility limit is, what is the solubility limit? The solubility limit is KSP, causing them to precipitate out the solution and form solid deposits. Common source of scaling in water system include hardness mineral like calcium and magnesium, which are present in varying concentration in natural water sources. Okay, a scale deposits can reduce the flow capacity of the pipes, decrease the efficiency of the heat exchanger and water heater, and lead to the clogging and blockage in plumbing system. Factors such as, again, same factor is also prevalent here for uh, mm, scaling also. Okay, so the corrosion of, if the water is undersaturated with carbonate in the system. Okay, because we know that when system is saturated with carbonate, it will form CaCO3. But so corrosion happens. Means you generally know that this iron corrosion means iron oxide is formation of this powdery form. Okay, I hope this is clear to you. A scaling in pipe may result due to water which is supersaturated with carbonate. So the option correct option is undersaturated and supersaturated. That is this. Corrosion is undersaturated with carbonates, whereas scaling is supersaturated with carbonate. Remember, this is a very important concept of saturation index. You should know this formula, SI and all these things. Okay. So next four question is related is a numerical question. So what is happening that a bar chart will soften, which may say hard water is with you and you have to soften it, and the desired level of hardness is 100 milligram per liter as CaCO3. Okay, if the lime of the if the lime and soda SS are assumed to be 100% pure, so you have to calculate the dosage of lime required is itna milligram CaCO, itna milligram as calcium hydroxide. Okay, dosage of lime as calcium hydroxide. Remember, this all data is in form of milligram per CaCO3. Okay, so now the dosage. So now what is happening that from this, if you are not clear, I will just zoom out. So see here it is 293, 293. So how can you read this graph? You can say that due to CO2 21 milligram per liter CSU hardness is due to hardness due to this CS this due to CO2 gas, that is carbonate, is 21.9 milligram per liter as COCO3. Due to calcium it is 238, and due to calcium and magnesium 239. Okay, so here it is a 0 point. So here I cannot write. Okay, so this is due to gas. Alkalinity is hardness due to gas, and this is due to dissolved ions. Okay, so now this calcium is this calcium is associated with chloride also, and this calcium is associated with bicarbonate also, and but magnesium is only associated with chloride only. Okay, so in the form of chloride only. Okay, so you can also say from here you can also say this alkalinity, this HCO3 minus will be responsible for alkalinity. So alkalinity is 198, and this chloride is not contributing anything to alkalinity, because we know that this chloride is not forming any kind of alkalinity. Okay, but overall this is this is how one should read this graph. Okay, so remember, this hardness is due to carbonate and non-carbonate both, and alkalinity is only due to this. Okay. Get this here. Hmm. Okay. The question is now you know that your this is 293, and you have to come 100 gram milligram per liter as CO3. So how much hardness I have to remove? That is 293.6 minus 100. So 193 amount of hardness I have to remove. So the question is how much calcium hydroxide, means how much lime I have to add. Okay, so the desired level of hardness is 100 gram 100 milligram per liter. I have to write it here. Oh no, 100 milligram per liter. Okay, CaCO 3. Okay, sorry, CaCO 3. And this will be milligram per liter as CaCO. Sorry for all this typo mistake. Hmm. So, therefore, the only calcium. Now remember, I have to remove only one. I have to remove 193 milligram per liter. Hmm. So therefore, only calcium carbonate hardness and CO2 need to be removed. Okay. So you can see that to if you only this much amount of hardness I have to remove. So out of these three things, miss up to what amount I have to remove it. So it is you can see that it is 20. Sorry, 21.9 is here, and something out of 193 it will be till here only 193 amount. Okay. Sorry, it is 198. So up to till amount I have to remove it. So only carbonate hardness and this CO2 I have to remove. So 21.9 plus 193.6 is this much amount of lime is required. So this much amount of lime is required. Okay, and this is milligram per liter. So remember one more thing. I have written directly. If you have gone through this water softening process, let me remember uh, 1 mole of this. Actually, I don't know how to explain this. So, if you have attended my first lecture or some, I have said this that gram equivalent of for any reaction is always equal. So, if you remember that concept that A plus B reacting and forming C plus D. Okay. So gram equivalent of A, B, C, D, and remember when we represent this thing as milligram per liter as CaCO3, it is representing equivalent. So the equivalent of this mgc milligram per liter as CaCO3 will be equal to the equivalent of milligram per liter as this lime, that is CaOH whole twice. Okay, so that's why whatever I have to remove, it will be equivalent to the required. Okay, so that's why I have written this thing, that is milligram per liter as CaCO3. Okay, and we know that equivalent weight is given by molar mass divided by number of electron transfer, and gram equivalent is given by given weight divided by equivalent weight. Okay. Uh-huh. So this equivalent weight of CaCO3 is, this is 40 plus 12 plus 48, it will be 100 divided by 2, because this calcium formation of calcium carbonate requires exchange of two electrons. Okay, so that will be 50 gram, and similarly equivalent of weight of calcium hydroxide will be 74 divided by 37. Okay, so this is mhm. So what will happen that you know that this much amount of milligram per liter as CaCO3 I have to remove. So and it is in the form of calcium carbonate. So now I have to convert into calcium hydroxide. So I will divide this by equivalent weight of this calcium carbonate, that is 50, and then multiplied by it by the equivalent weight of this calcium hydroxide. So what will happen that this unit will change from milligram per liter as CaCO3 to milligram per liter as CaOH whole twice. Okay, so I hope this is clear, and from this equation, from here, you can calculate the total line required. Okay. Okay, so just I will discard. I will just go through the second. Hmm. So here, hmm, hmm. Here you can see what I said. This thing I was saying. Na, one thing na for this thing I have already you know this molarity is this divided by this. equivalent weight. I was just focusing on this thing, equivalent weight and normality, and this normality. So see here, this equation is there, that Na2SO4 is giving to Na plus, and here you can see that this equivalent weight. This is, sorry, gram equivalent. Sorry, not equivalent weight. If you have said something wrong, sorry for that, but you can see this thing, gram equivalent for all this thing all these three are equal. Okay, so and this is being represented in milligram per liter depending upon the unit. So suppose there is a question that how much for removal of this, how much this is required, and the equivalent weight of this is given. So you can just back calculate, uh, you can do a reverse calculation, and you can find this thing, how much sodium is required and all this thing. Okay, this is very similar to what I am discussing here. Okay, so this thing I have done here also. Okay, this thing I have changed this milligram. Now what I have done nothing but just I have converted this gram equivalent to gram equivalent to normal weight. Yeah, equivalent number of equivalent, and number of equivalent can be multiplied with the other required weight, and that will give you equivalent weight in the form of this thing. The amount of soda ash required is, okay, there is no need to remove non soda. Why soda is required? Because soda is required to remove non-carbonate hardness, but you can see this in this question. I have to remove this hardness till here only. I have to remove the hardness till here only. There is no need to remove hardness due to chloride. So there is no need to remove this non-carbonate hardness. Hence, there is no need to add any kind of soda. Okay. So there is no need to remove non-carbonate. The amount of soda required is milligram per liter. I hope this is clear to you. Remember, I have to remove this hardness till this point only. Okay, this point only. So that's why I am not adding any kind of soda. Okay, now see in the question what they were saying that here it was 100%. Now they are saying that this lime is not 100% pure, only 76% is pure. Okay, so if the purity of lime purchase is 76%, the dosage of lime required will be in milligram. So purity of the lime purchase is 76%, that is 0.76. Pure, now this is a linear combination, that pure lime required 157 milligram per liter as CSU3. I am very obsessed with this writing unit. So whenever I see any kind of mistake in unit, I will just correct it for at that moment only. Okay, so for pure lime you can see that for pure lime 159.47 milligram per of CaCO3 is required. Now you can say that now purity has decreased from 100 to 0. Means you have to add high amount of soda, a high amount of lime, because we need this much, and it is only 0.76%. So the 76% pure lime required will be this divided by 0.76, that is 214 214 uh, 214.11 milligram per liter as CaCO3. Okay. Hmm. The second question is, using the above bar chart, calculate the dose of lime required for per daily meal if the desired level of hardness is only 50 gram of milligram. Now see, they have said that this thing, instead of 100 milligram per liter, the desired amount is 50. So initially 293 is there. So now what how much How much I have to remove? 293, 293 minus 50. 293 minus 50, it will be around here. 293, it will be 254, so it will be around here. So I have to remove this much of hardness. Carbonate and non-carbonate, both kind of hardness I have to remove. See, this is very easy question, but very interesting question to understand the concept of hardness. Okay. The desired level of hardness is 50 milligram per liter. Therefore, the hardness to remove is 293 milligram per liter. Okay. Therefore, the calcium carbonate hardness and calcium non-carbonate hardness. Remember, here we have to from this question you can see that I have to remove the calcium hardness also, magnesium hardness also. I hope this is clear to you. And from the graph you can see that what is calcium hardness. CO2, calcium carbonate hardness, calcium non-carbonate hardness. So the first question is what is this due to this CO2 it is 21.9. It is 21.9. Okay, it is 21.9, and this carbonate hardness is 198 because it is 0 to 198. Okay, and 198, and you have to remove only this 295 minus 50. So you can subtract from here, and if you do this calculation, you can find out this non-carbonate hardness is only 50. Okay, how this, remember, and this non-carbonate hardness is again substitute again divided into three things. One is, actually you have to do, just let me do one calculation. Mm, Calculator. So I have to 293, from 293 6.2 I have to go 243. Okay, 243 hardness I have to remove. So obviously 243 point 243.6, 240, out of which 20 minus 21.9 is due to 21.9 is due to this CO2, and 198 is due to this calcium carbonate hardness. So how much left is 21.3. Okay, and out of and how much total calcium is there? 238 is due to calcium. Okay, 238 is due to calcium. So what you can do is 293, 293. So 238 minus 238, 238 minus 198, 198, how much is 40, and what was remaining, it was around 43. So you can see this, and I have to do it till here. So this calcium 198 is giving 198 is giving is due to calcium carbonate and carbonate hardness, and this minus this will be contributing to non-carbonate hardness, and this much amount is due to magnesium non-carbonate hardness. And how much this is, you can substitute by 293, how much, 293.6 minus 50 minus 21 minus 238. So if you do the calculation, you can see that it is around 5.6. Okay, I hope this is clear to you how this is how this 40 is calculated to 5.6 is calculated. And here you can see calcium due to calcium 21.9, carbonate hardness 198, uh, 198, 198, and due to this magnesium non-carbonate hardness it is 5.6. The total will be 225.5 milligram per liter as CaCO3. And you know that this equivalent weight of CaCO3 is 100 divided by 2, that is 50 equivalent. And again you have to remember, in this question they were asking to convert in the form of CaOH whole twice. That's why I have written the formula of CaOH whole twice. But in this question, they are asking you to convert in the form of, sorry, they are asking you to convert in the form of CaO, that is 56.228 gram. So again, what I will do, I will divide with the help of equivalent weight, and you will get the number of equivalent, and again you will multiply it by 28, so you will get the total lime required. So 225 into 28, 28 is the equivalent weight into divided by 50. Remember, the first we have divided by 50, then multiplied by 28. So it is giving to 126.28 milligram per liter as calcium oxide. Okay. Hmm. Coming to the last question of the day. Last question of the day is using the above given bar chart, calculate the dosage of soda as required per day in milligram per liter. Remember, now they are asking in milligram per liter CaCO Na2CO3. Here they were asking milligram per as CaCO. So this is just equivalent. And now why they are asking in the form? Because generally when we remove hardness, you will just purchase this much amount of Na2CO3 from the market. You will purchase this much amount of calcium. You will go to the market, they will say that the purity is 90% or 76%. So according to your calculation, you can purchase it and you can use it directly in your system. Okay. Again, the soda remove the calcium non-carbonate hardness. Remember, here we are asking you to remove this non-carbonate hardness. Okay, and magnesium non-carbonate hardness. So total soda required is 50 plus. Remember, in this question, the it was, remember in this question they were, as the limit was 100 milligram per liter, so there was no need to it was see, the desired was only to remove here when the effluent is one means effluent is 100, so it was till this point only, so there was no need of to remove this non-carbonate hardness, and we know that this soda, that is NO2CO3, is to remove non-carbonate hardness only. But as the as effluent was 100 milligram per liter, and it was, I have to remove the hardness still here, so there was no need to remove non-carbonate hardness. But now what happened, that they are asking you to go to this 50, means from 293 to 50. See, remember this question is 50 milligram per liter again. 50 milligram per liter. Okay, 50 milligram per liter. So now I have to, from here to where I have to go, I have to go here. So miss, for removal of non-carbonate hardness, I require some other thing, that is, remember, only this much non-carbonate hardness is how much, this much plus whatever area is in this thing. We will calculate it, and we have already calculated this thing. Okay, how much we have calculated it? hmm. uh, we have calculated this 40 plus 5.6. Okay, I hope this is clear to how this 40 and 50, and this was in the form of calcium carbonate. Okay, so equivalent weight of calcium carbonate is 100 divided by 2, that is 50 gram, and equivalent weight of Na2CO3 is 106 divided by 2, that is, oh, it will be 53 gram. Is it clear? Hmm. So again, I will divide by its equivalent weight, then multiply by its equivalent weight to get the desired soda level. Okay. So till now I have discussed all the question. I have some slide related to adsorption, but I think for now I won't be discussing it because I don't have time. Only 5 minutes is left, and this cannot be discussed in these 5 minutes. So I hope this is very clear to you how much time I have taken. 1 hour 56 minutes. So no one has joined. So that's why I'm ending the lecture. You can always access this lecture on the YouTube channel. Okay, so thank you for the today session. I'm closing the meeting.